Thank you, Balazs. Hi, everyone. My name is Amna Chaudhry, and I'm working as Senior Research Associate on Levitate project at Transport Safety Research Center in Loughborough University. I welcome all of you to a Levitate webinar on policy interventions. We have five speakers here, and who will be introducing themselves when they start their presentation. Before I start the session, I would like to mention that this webinar is being recorded, and if anybody has any disagreements, we respectfully ask them to leave the webinar at this point. Also, for any questions, please use the Q&A function that you can see at the bottom. And for any general comments or feedback or any generic questions regarding the project, please use the chat function. With that, I will invite Professor Andrew Morris from Loughborough University to provide a brief introduction to Levitate project. Over to you, Andrew.
Thanks very much, Amna, and a very good afternoon to everyone. Welcome to this Levitate webinar. My name is Andrew Morris, and obviously I'm joined by colleagues who are also involved in the Levitate project, who will introduce themselves to you shortly. So in the webinar today, we're focusing on potential policy interventions relating to future connected and automated transport systems. But first of all, before we look at some of the specifics of the analysis that we've been doing in that regard, I'm going to give you a brief introduction to Levitate, so you can understand the overall aims and objectives of what we're trying to achieve. And then I'll hand over to Amna, who will present some of the results of the project to date in more detail. So Levitate stands for Societal Level Impacts of Connected and Automated Vehicles. And the intention is that the project will build tools to help European cities, regions and national governments to prepare for a future with increasing levels of automated vehicles in passenger cars, urban transport services and urban logistics. The project funding is 6.4 million euros provided by the European Commission in Horizon 2020 research framework. And the project has been led by ourselves at Loughborough University. And it brings together 12 partners from 10 countries, including renowned research institutes, local authorities and global partners. And it's a 3.5-year project which started in December 2018. So I mentioned that it involves 12 partners in total. The partnership addresses a combination of technical, stakeholder and implementation challenges involved in conducting the necessary research to prepare what we're calling a policy support tool. The team is also assembled in order to carry out all of the necessary competencies and expertise in order to conduct the technology evaluations through data analysis and simulation, and to ensure at the end of the day that we have successful dissemination and exploitation of the project results. And then ultimately to successfully launch the policy support tool to be used by a range of stakeholders, including local and national roads authorities and policymakers. Therefore, we have a blend, or an excellent blend, of research institutions, universities, software and simulation experts, and road authorities. Overall, I guess there are quite high expectations associated with quite a lot of optimism about what connected and automated transport systems might deliver in terms of safety, mobility, and environmental impacts. But as we've seen yet, there's no standard means to predict what is really likely to happen, and whether all of the predicted benefits are likely to eventuate, or whether there may be issues associated with the introduction of automated transport systems that we've not yet realized or anticipated. And maybe less obviously, we need to consider whether the potential benefits that we might predict in one particular metric do not mean that there's a detrimental impact on another metric. So we need to consider all of the likely benefits and disadvantages collectively. Now, this sort of analysis is a little bit more complex than you might imagine, but it's no less important or necessary. So the overall aim of Levitate could be described as building the tools that will help European cities and other cities for that matter, regions and national governments prepare for the future with what is predicted to be increasing levels of automation in passenger vehicles and other urban transport services and urban logistics for that matter. We'll eventually develop an impact assessment framework which will be available to policymakers so that they'll be able to manage the introduction of automated transport to maximum effect. And this in turn will allow the technology that can be harnessed in order to achieve societal objectives. To achieve its objectives, Levitate is establishing a number of impact assessment methods. And the intention is that we will establish how these can be applied across a wide range of possible future scenarios once automated vehicles become a reality, based on stakeholder inputs, quantification of impact dimensions and indicators, and development of micro-simulation models. We're then exploiting these methodologies to examine what might happen within each possible scenario based on modelling and simulation. So, for example, we might want to consider how driverless cars will impact on parking provisions within inner city areas. And we might want to determine what the likely traffic flow into city centres might be if we decided to provide dedicated lanes for driverless cars. And once we've looked at a broad range of use cases and sub-use cases, we're going to bring all the individual analysis together through the establishment of what we call a policy support tool. And essentially the tool will be available to city authorities and policymakers to assess the impact of a particular scenario. Say, for example, congestion, based on changes that are likely to take place as the automation becomes more prevalent. And this will allow policymakers to study how congestion in inner city areas might change on different roadways if the composition of the vehicle fleet changes as a result of changes in the uptake of autonomous vehicles. So once the policy support tool has been completed, it will be available for general usage, and a project will thus engage in focused dissemination activities which are designed to inform stakeholders of the availability of the tool. And with that, I'll hand over to my colleague, Anna Chowdhury, who's going to present some of the results of Levitate in a bit more detail for you.
Thank you, Andrew. I'll just share my screen. I think you'll have to stop sharing. I hope you all can see my screen. So I will just be following the introduction provided by Professor Andrew. I will just I would like to present an overview of the assessment methodology within Levitate project. So we have three major categories based on the different transport modes, including urban transport, passenger transport, and freight transport. We term them as these categories as use cases. Under each use case, we have further subcategories, or which basically are different policy interventions applicable under that particular use case, which we term them as sub-use cases. For example, under passenger cars, you can see these variety of sub-use cases which were being tested and analyzed in this project, varying from infrastructure-related policy interventions to parking-related interventions and automated ride-sharing services. Under urban transport, two major policy interventions were tested, including point-to-point automated urban shuttle services and on-demand automated urban shuttle services. And under these categories, there were further sub-scenarios which were analyzed, depending on their operations. Under freight transport, we have analyzed automated urban delivery, automated consolidation, hub-to-hub, and platooning on bridges. And to analyze the impacts from different policy interventions, we have made use of different methods, different applicable and suitable methods. which range from microsimulation to mesoscopic simulation, system dynamics, wherever it was applicable. We have also made use of operations research, which is widely used for freight transport and related research, and also microsimulation as well. With regard to how these sub-use cases or policy interventions were selected or identified, we had gone through several discussions with the city officials and industry professionals to identify and prioritize these policy interventions, which are of higher importance. So this is, in today's webinar, we will be focusing on passenger transport sub-use case, and we will be covering some of the policy interventions under passenger transport, including road use pricing, dedicated lanes, replacing on-street parking or parking space regulations, and parking pricing. Before I hand it over to our first speaker today, I would also like to briefly talk about a general approach within the project on the consideration of future automated vehicles, since there is no real-world data available. So we can only make use of the best knowledge which is available through existing literature. So our approach within the project was that we considered two types of CAVs, two types of connected and automated vehicles, belonging to first generation and second generation. And they both differ from each other on the basis of their ability. For example, second generation vehicles will have much advanced technology, and they will have much improved and advanced sensing and cognitive ability, decision making, driving characteristics, and anticipation, for example, of incidents. So these two types of CAVs have been modeled throughout the project and under different policy interventions, which will be presented by our speakers shortly. We already have, this is an overview of program which should have come earlier, but nonetheless, we have already covered introduction and overview of assessment approach. These are the main policy interventions which will be presented today. And then there will be final remarks on the webinar. So with that, I would like to invite our first speaker, Gerald Richer from Austrian Institute of Technology, to present some of the key findings from road use pricing policy. Over to you, Gerald.
So unfortunately, there is a problem with Gerald. He is not listening to us. So I would suggest to go forward with another presenter, and then we try to figure out what's happening with Gerald.
Okay, that's fine. I can then move on to next presentation, which I myself will be presenting, which is on analyzing the impacts of dedicated lanes on urban highways. This is just an overview presenting network characteristics and analysis scenarios for analyzing the impacts of dedicated lanes on urban highways. We have used Manchester network, a network within Manchester area, to analyze the impacts of dedicated lanes. And this network involves a major arterial called A6 road and a motorway called M602. So this served the purpose for estimating the impacts of, for deploying and estimating the impacts of dedicated lanes. In terms of analysis scenarios and various placement options, we have tested the placement of dedicated lane on motorway only, motorway and A road both, considering leftmost lane placement, A road rightmost lane and leftmost lane placement. Just to brief regarding our microsimulation approach, within Levitate, we have used Aimson microsimulation. And with regard to CAVs deployment scenarios, we have considered automation of both passenger cars and freight vehicles, and our deployment scenarios vary from 0 to 100% market penetration rate of CAVs with 20% increments. These are some of the key parameters which we use to define behaviors of CAVs in microsimulation. which range from car following behavior to acceleration, deceleration characteristics, overtaking behavior, lane changing behavior, behavior at signalized and unsignalized intersections, and anticipation of obstacles. We have a wide variety of impacts that we have analyzed within Levitate project, but in today's presentation, considering the time slot that is allocated, I will be presenting some key findings from the work that has been done so far under this sub-use case. So first of all, impact on travel time. Before I start commenting on the findings, to understand the plot, on the x-axis you can see CAV's market penetration rate scenarios, and you can see three numbers where first number belongs to percentage of human-driven vehicles, second number to percentage of first generation CAV, and third number to percentage of second generation CAVs. And these four scenarios were considered where that provision of dedicated lane is applicable, because of course at 100% manual driven vehicle scenario or 100% automated vehicle scenarios, there's no need to provide dedicated lane. So in terms of the results that we got, you can see these, the darker line represents the baseline trend. So which means that the impact on travel time due to increasing automation only without any dedicated lane, while the other colored lines present impacts on the basis of different scenarios which were tested. Overall, we can see that maximum travel time saving benefits were identified in this scenario where the dedicated lane was placed on the leftmost lane on A road. Also, it's important to note that we only considered so far one dedicated lane within the analysis scenarios. So for example, with increasing market penetration rate, of course, it can be expected that there would be need for maybe another for two dedicated lanes to improve operation, or maybe with increasing or with much higher penetration rates, and where their human-driven vehicles percentage become lesser, there may be need to put human-driven vehicles on dedicated lanes. So these things have not been modeled or analyzed. These findings just correspond to considering one dedicated lane only in the network that we used on motorway and A road. Overall, we can see maximum reduction at A road leftmost lane case, and maximum benefits were found at a moderate scenario. That is also explainable, not at low MPR or high MPR scenario. We also found that our studies, our results generally are consistent with some of the previous studies conducted to analyze the impacts of dedicated lanes on travel time. Within Levitate, we have used several different approaches for analyzing the impacts. And I'm presenting this one result from our Delphi study, where opinion from experts was taken to forecast or to foresee the impacts of future policy interventions. And we see that from experts' opinion, we see that they perceive that there will be progressive reduction of travel time with increasing market penetration rate with when we provide dedicated lanes, and maximum reduction can go up to 24.5% in case of the innermost motorway lane. The Delphi study was conducted in two parts, first round and second round, and we also found that second round participants also, in majority of second round participants, showed agreement with the results of first round. One common thing that was observed from Delphi study results and the microsimulation results was that the innermost lane placement was found to be and was identified to be the most optimal one in terms of travel time savings. I would like to present results from the safety impacts. But before I present results, I would like to just present an overview of surrogate safety assessment that we performed to analyze safety impacts. So this approach basically makes use of microsimulation output, where we make use of vehicle trajectories from microsimulation output. And after identifying different vehicle types and using the FHWA surrogate safety assessment model and giving TTC threshold values, we can identify traffic conflicts or potential collisions. But we, in addition to identifying traffic conflicts, we estimated crashes using a probabilistic approach proposed by Professor Andrew Tarko, and estimated crashes using that approach. These are the results that we obtained after applying that approach, which I presented in my previous slide. And we can see overall that the safety was significantly improved with increasing market penetration rate. Again, maximum reduction in crashes can also be observed at A road leftmost lane scenario. And since we only tested one dedicated lane deployment case, but studies suggest with higher market penetration rate, 2 dedicated lanes for further improvement in safety. We also have results from emissions. These are also microsimulation results on emissions. And you can see with increasing market penetration rate, there is significant reduction in emissions as well. However, an important thing to note is the major part of reduction in emissions is coming from the fact that we have considered electrification of cabs. So with increasing electrification, there will be, of course, reduction. With more and more cabs in the system, there will be reduction in emissions accordingly. These are some of the key findings, or I'm just summarizing the findings, which I pretty much covered already. But just to give a quick recap, again, we found increased benefits under motorway and A-road case as compared to motorway only. So that means deploying, providing dedicated lane both in the major arterial and motorway can potentially provide added benefits than placing it on motorway only. And we, in terms of the placement strategy, we found that leftmost lane placement indicated the maximum travel time savings as compared to the right side placement or rightmost lane placement. And also, again, since we tested just one lane, one lane for the dedicated lane analysis, we found that moderate scenario indicated maximum travel time savings. And moderate is 60-40-0, where 60% of vehicles were human driven and 40% first generation cabs. Same goes with the safety benefits. And we also found environmental benefits overall, but that, of course, the major impact is due to the electrification of vehicles. These are some of the references that were used. That's all from my side. If there are any questions, I can check the chat box. I can maybe stop sharing and see if there are any questions so far. In the chat, I don't see any questions, and in the Q&A also, I don't see any questions so far. Can I move on then?
Yeah, indeed, I don't see any questions, so I think we can move on and try. Gerald wrote that maybe he is able to present at this point, so we should try with Gerald.
Okay, can I invite Gerald if you can, well, if you are here?
If you can hear me.
Yes, but the volume is quite low.
The volume is low.
Yeah, no.
Better?
Yes, much better. We can hear you.
Okay, great. So I will share my screen. Can you see my screen?
Yes.
Yes.
Okay. Well, thanks for the opportunity to give you an overview on our efforts to understand the implementation of road use pricing as a measure to exert some control on the use of personal cars in general, and especially in the given context on connected automated vehicles. We have been using the following ideas that drive our work, and the major aspect is that we're interested in how people will react to this introduction of automated passenger cars. What the effects will be when you implement road use pricing measures, and how will this affect the choices of transport modes? That means including all modes of transport, even with cross-modal trade-offs that might occur, and which approach is most beneficial. The basis should be given for decision makers, and it should support road use pricing as a measure to achieve various regional goals that might depend on the city or the region that wants to implement this. We're in the process of working out the detailed effects and consequences, and I want to draw general conclusions for comparable cities and sites and regions. Our model and the region is concentrated around the larger area of the city of Vienna. It uses MATSIM as a simulation framework, which is an agent-based activity chain simulation. We utilize a calibrated traffic model and do have a calibrated mode choice model as well, and implemented some in-house extensions to allow for multimodal trip compositions. The region is around 60 kilometers in diameter around the center of Vienna, and the inhabitant population of this area is around 2.85 million people above 18 years. The mobile agents that we're simulating are around 200,000, which is roughly 12.5% of the mobile population in that area. And we look at an average workday scenario. So the road use pricing area, that is the area where we implement road use pricing measures, is this rose-colored area, which is the inner city, everything within the inner city. In the darker purple color, you see the city center, the actual city center, which is contained within the inner city. And the inner city is bounded by a ring road. This is the dashed blue line here in the lower schematic diagram. And at the limits of the city, that is the outline of the bluish area, is also the limit of our investigation perimeter. So we basically look at all the impacts that concern everything within the city. The region that is outside of the city is the feeder area that provides the boundary conditions for everything that happens within inside the city. We chose two implementation scenarios for this road use pricing. One is the static toll on all vehicles. That means we charge on entry of vehicles into the inner city, into this rose-colored area. So vehicles more or less drop a certain amount of money when they cross the border. And the pricing levels we chose were 0, 5, 10, and 100 euros, where these 100 euros are the prohibitive scenario, which more or less gives us an impression on what happens if the full extent of the measure is implemented. The other implementation scenario is the dynamic toll on all vehicles. So we charge per unit distance within this rose-colored area, within this tolling area, and the pricing levels are again 0, 5, 10, and 100 euros. But in this case per 7 kilometers of traveled distance. That means if a vehicle decides to cross the whole rose-colored area as diametral route, it will pay the same amount of money as in the case of the static road use pricing. There are several assumptions that we're using for the modeling of road use pricing, and one central concept is the value of travel time savings. One can think of this as how high is the value of the time you spend traveling, for example, by car. So how much would you like to replace this time by doing something else? You can also think of it as the inconvenience of using a transport mode, because your attention is bound when steering the car. So this causes some inconvenience. For example, as a reference, public transport is at about 50% of this inconvenience or value of travel time savings of a conventional personal passenger car, conventional vehicle. The automated vehicles of generation 1 and generation 2 are at 80 and 75% of the VTTS of a conventional car, respectively. And these values of travel time savings do influence mostly the agents and their travel decisions. We assumed also that the traffic throughput of the road network will be automation dependent. So the higher the market penetration of automated vehicle gets, the more traffic throughput you will have on the roads. We used some simulation results that were derived within the project by macroscopic simulations. But if you want to think about it more or less in the terms of first principles, you can think that the conventional vehicles, as is depicted here, do have a certain headway distance to their leading front cars. And if you introduce automated vehicles that are expected to be able to react much faster than humans, you can reduce this headway distance, of course. So assuming the same speed, you can immediately see that more cars can pass through within the same amount of time. The impacts that we defined to investigate are at 1, the travel time, which is defined as the average time of a trip within the inner city to cover 5 kilometers of distance by using any mode, which is the average over all modes that are included. The travel distance is the average of all agents' daily travel distances by using any mode within the city. And the use of active mode is the share of travel trip distances by active modes. That means walking and cycling being defined as the active modes. And that in relation to all transport modes within the city. And the same for the public transport. So it's the share with respect to distance that has been covered by public transport. Again, compared to all the transport modes and distances within the inner city. If you look at the results, there are a few remarks that you have to consider. What I will show you is an excerpt of results that provides a more abstract view. It is not only a car-centric view and includes all modes with the mentioned cross-modal trade-offs, and the impacts are by definition highly aggregated. So if you look at the average definition of before of the travel time, averages can be deceiving. This is again not including trip emissions with respect to sufficiency aspects. By sufficiency, I mean here that it is not being considered that trips might be dropped if they are less necessary, which also would be a considerable impact on the results. The trip modes have to be defined for a trip, and we chose that which is mostly used because a trip can be composed of several stages that is using different traffic modes. You always have a first walking stage when you try to get to the subway or the bus. But what we do to clarify, to define the modes of our trips is we use the longest distance travel mode. That is that mode which has covered the most distance as part of the trip. And on the side, you see an example of one of those multi-stage trips, where at first in the lower left you have a short walking stage that reaches the purple-colored public transport, and then again some walking stages in the middle later on. For the results, when we look at the static road use pricing, which is again, as a reminder, given to the lower right, we drop more or less an amount of money when we enter the tolling area. We see a slight reduction of the average travel time with increasing car penetration or automated car penetration rate from the left to the right. We also can see from the blue to the red line that we have a increase of about 2.5 minutes when going from the status quo case as it is now without road use pricing to the maximum level of 100 euros, which is the red line. When looking at the dynamic road use pricing, an interesting effect occurs where you can see that people are willing to exchange what they would have to spend as tolling fees for an extra amount of travel time that they have to invest. So the static, the basic case as it is now is again the blue line. And when you go to the middle levels of road use pricing, which would be 5 and 10 euros, represented by the green and orange line, the travel distance increases strongly to the upper levels. But when you reach prohibitive road use pricing levels of 100 euro at the red line, the average travel distance is very much down again. Again, we have a look at the active mode split. You can see a progression from no road use pricing up to the prohibitive case of road use pricing of 100 euros, where the share of total distance by active modes increases by around 4% in total. While staying more or less the same, represented by those flat lines with increasing automation levels. And here we see the last case for the dynamic road use pricing, how the public mode split is assumed to evolve with increasing road use pricing levels from the blue line to the red line, and again from left to right with increasing automation levels. You see a slight decline here. So what we can see as emergent findings are most importantly that the travel time average will agreeably be reduced if you introduce static road use pricing and increase the market penetration rates of automated vehicles, which would be the left upper case. We also see minor reductions of travel time average for the dynamic road use pricing case. And for the travel distance averages, we see that dynamic road use pricing with increasing market penetration rates of AVs will lead to rebound effects where people don't behave as you would intend to cause as an effect when introducing your measures, your road use pricing measures. Also, for active mode distance share and passive mode distance share, you have those agreeable effects for the prohibitive cases, where you get an increase in active mode share of about 4% for both prohibitive and extreme implementations of road use pricing, and for the passive mode distance share, you can see the same. There is an increase in 15% and for static road use pricing and dynamic road use pricing. But overall, it seems that dynamic road use pricing implementation is a bit less predictable and allows more room for the agents, at least, and with persons it won't be less likely to see unwanted rebound effects and unwanted phenomena occurring that mostly will be there to circumvent those measures. The static implementation looks more stable in that respect and seems to be better fit to actually reduce passenger car use. This is about it. So if there are any questions, please.
Thank you, Gerald, for providing quite interesting and insightful findings from road use pricing policy related work. I would see if there are any questions for you. I can't see any questions specific for you, but there was a question for me that whether in our case, dedicated lanes in dedicated lanes presentation, does the leftmost lane mean the fastest one? Which I answered already in the chat, that in our case, rightmost lane is the fastest one. And also I see a question, a generic one, which everybody's welcome to contribute as well, which by Jacob, asking what would be your team's recommendations for the Law Commission as it finalizes their work on the legal framework for cabs in the UK, what areas they should focus on in immediate future without going too much into abstract future speculation, and what areas are key to get any future regulation right. I did answer to it that saying that it is first thing which is really important is to consider societal level impacts and not just one particular impact, which we are also considering within the Levitate project as well. So societal level, wider level impacts, and considering all sorts of various impacts that can be potentially there. And also we are, through our findings, we are identifying that the transition phase is of high importance, and through right policy decisions, any potentially adverse impacts can be mitigated. And some of the results which Gerald shared regarding road use pricing policy, and my other colleagues will also be sharing, they would also present their recommendations that fall under each different several policy interventions, for example, related to parking, the pricing policy, parking space regulations, and also road use pricing related, Gerald already covered. So this is my response to it. If anybody would like to add into it, please go ahead. If not, I don't see any specific questions so far for Gerald, but if it does come, Gerald, I'll get back to you with that. And I think we can now move on to our next presenter, who is Hua Shah from Loughborough University, and she will be talking about impacts of some of the parking space regulations. So Hua, over to you.
Yes, can you see my screen?
Yes, I can see you. We all can see.
Yeah, good. Okay, good afternoon. My name is Hua Xia. I'm a research associate in Loughborough University. And I'm going to talk about the replace on-street parking sub-use case in Lavated project. So this is replace on-street parking with driving lane, cycle lane, public spaces, and pickup drop-off points. And from this sub-use case, we try to show some insights, such as when autonomous vehicle come into the real world, how can we space our cities and start to rethink how to best use of the on-street parking space. The idea is that the introduction of the autonomous vehicle offers potential to reduce the urban space requirements for road and parking and create more space for high quality life area. So this sub-use case could bring this outcome and benefits like the increased capacity, improve congestion, reduce air pollution, improve safety, and more efficient use of parking spaces. And also we use these indicators and measures to quantify the impact, such as capacity, travel time, delay time, mean queue emission, and conflicts. And in this sub-use case, we are using Leicester City model. Leicester City is in the Eastern Midlands and very close to Loughborough University, where we are, just 20 minutes driving. The Leicester City center model area is around 10 square kilometers. The simulation consider lunchtime rush hour, which is 12 to 1 o'clock in the afternoon. And all disabled on-street parking is kept in place, which means we are not going to replace the disabled parking in the modeling. In this sub-use case, we have 6 scenarios. The base scenario with CAV implementations without replacing the on-street parking interventions. And the case 1 remove half of the on-street parking spaces. And the rest of the case is replace on-street parking with driving lane, cycle lane, pickup drop-off points, and the public spaces. This is Leicester City Centre on-street parking area. For some practical purpose to be more effective use the simulation, we divide the whole city centre into 4 parking zones. You can see the zone 1, zone 2, zone 3, zone 4. There is a total of the 52 streets and 138 parking bays, and around the 700 periodic section incidents have been set in the modeling. For removing half of the parking scenarios, we try to remove the parking space equally from each of the parking zones. And in the end, there are 28 streets, 70 parking bays, and around 400 periodic section incidents remain in these scenarios. And this is on-street parking information from Leicester City Council open data. And you can find all the on-street parking information here, such as street names, type of the parking, number of the parking bay, limited parking time. With this information, we can find the street and the parking bays from the Google Map. Because of this COVID situations, we couldn't go to site and have the site investigations, but we can have the information from the Google setup map. For example, in this 12th Street, we have 4 parking bays with different lengths. So we can use all this information for network coding, such as the location ID for each of parking bay in the modeling. And in the simulation, we use the function of a periodic section incident to simulate on-street parking. This is the only approach that can simulate on-street parking currently in Anson. The function can simulate on-street parking, a goods vehicle loading and uploading, a taxi picking up and dropping off a passenger. So periodic section incident is kind of the traffic incident that block the traffic over a certain of a time. And this action creates and random incident and placed randomly throughout the area. And here the result for traffic performance. At the top, the figure shows absolute value of the travel time and delay time for baseline and the intervention based on the CAV fleet market penetration. As you can see, as the CAV market penetration increased, the travel time and the delay time decreased. At the bottom, the table shows the impact from each of the intervention. It is clear to be seen the intervention of replace parking with driving lane, cycling, and replaced with the public space have shown a significant improvement compared to the intervention of remove half of the on-street parking and replace them with pickup the drop-off points. And this is to be expected as the intervention of remove half of the on-street parking and replace them with pickup drop-off points may often create stops and the queues in the traffic due to the frequent parking maneuvers or vehicle picking up, dropping off passenger, and needing more congestion and delay. So for environment impacts, the results are very straightforward. You can see as the CAV market penetration rate increase, the emission for all the CO2, NOx, and the PM are reduced. So this is to be expected as all the CAVs were considered as an electric CAV. Also, the capability of CAVs are expected to travel at a consistent speed, and that leads less stop and go situation in the traffic stream, which would in turn reduce emissions. For safety impacts, the crash are reduced significantly for all the intervention. As you can see, there are more than 90% reduction when CAVs reach 100% market penetration rate. However, there is no significant difference between the interventions. So in Innovative project, we have other methods to assess the impacts, and Delphi is one of them. In here, I just pick up two indicators that we can have the comparison with the result from the max simulation with Delphi. For travel time, the first round of Delphi result showed that there will be a small reduction of travel time for the long term, and around like just 7% can be achieved at 100% CAV market penetration rate when on-street parking is replaced with driving lane. For second round, the general expert opinion indicates that replace on-street parking with public space, driving lanes, and the pickup drop location will not affect travel time. So this is inconsistent with the result from the max simulation method. For amount of travel, general expert's opinion was that the introduction of CAV in the urban environment will increase the amount of travel, like replace on-street parking with driving lane will lead to increase of 18% of amount of travel for the 100% market penetration rate. This is quite close to a result from max simulation. We have the 17% increase for the 100 market penetration rate from the simulation. So this is key findings from this abuse case. So compared to the baseline scenarios, a reduction in travel time and delay time can be expected for all interventions. In general, replace on-street parking with driving lane, cycling, and public spaces show a better performance compared to remove half of the on-street parking spaces, compared to remove half of the on-street parking spaces and replace them with pick-up drop-off points. The traffic performance results are not consistent in terms of the automation because we have some wiggly shape, and probably because the interaction between the mixed type of vehicles we have the first generation, second generation mixed with conventional vehicles. And the better performance occur at the mixed scenario, like 40-40-20 for baseline and most of the intervention. So that maybe suggests the combination of 40-40-20 might be suitable for this abuse case. And also the intervention of replace by pickup drop-off points tend to generate a queue in a traffic stream while vehicle picking up and dropping off of a passenger and causing congestions. So dynamic pickup or drop-off points could be introduced in the network as improvement measures. And finally, the result also suggests that replacing half of the on-street parking spaces might not provide the expected improvement to the traffic condition in the city center, especially with the congestion network. So this is all from my side. So is there any questions?
Thank you for presenting some findings from parking space regulations. If there are any questions, let me see. I don't see any additional questions so far, but I probably just to add in the last question received from Jacob, I was trying to add into that typing my answer, but maybe I can answer that live as well. Just to add in my previous response, I would just like to highlight this again, that as when I presented an overview of assessment approach within Levitate, the sub-use cases or the different policy interventions tested under the project are those which were identified and prioritized through discussions with several stakeholders, including city officials and industry professionals. So these are also already the areas which should be on focus. So just to add in your question. So no questions so far for Huasha specifically, then probably we can move on to next presentation, which is by Mohit Singh from Loughborough University, who will be talking about parking pricing related strategies. Mohit, over to you.
Good afternoon, everyone. Can you all see my screen?
Yes, we can see.
Thank you. Good afternoon, everyone. I am Mohit Kumar Singh, and I am a research scholar at So I will be going to discuss some results from the parking policies and how it affects those key performance indicators, those my earlier colleagues have shown you. So this is a small background about the parking policies. Why do we need them? So these are some methods listed, but yes, there could be some other methods. So like to tackle higher volume of traffic, to enforce public transport, and to increase state's income, and for to reduce traffic, to reduce emissions and improve the traffic safety. In case that I will be discussing in upcoming slides. So we are going to see what would be the impact of different parking conditions, and we will be getting those with the help of these KPIs. Here we have not included all of them. We have in traffic condition, we have taken travel time. In emissions, we have taken these, and in safety, I will be just showing the crashes. So this is the that taken into consideration in this study. It has 108 nodes, 38 sections, and it was simulated for evening peak hours of 3 hours. It includes public transport and cars. And these are the those were introduced simulation. So These are 4 listed here. In first one, the car enters and parks inside the area. So wherever the passenger is in the same place, there will be some parking area just shown here in this circle here on the top left. So people will drop their passenger there and they will park there itself. In other scenario, they will enter and they will drop off and return to the origin to park. So there will be some parking locations. They will drop the passenger and then they will come to those parking locations and park there. In third scenario, we can see that it will drop off the passenger and return to the outside parking. And in fourth one, it will enter and it will drive around. So what it will do, suppose the passenger has got down and nearby the vehicle will roam till the passenger is ready again and ready to go. So these are the proportions of all those scenarios we have shown earlier. So in no policy intervention, we are saying that all 100% passengers will park their vehicles inside, and in others, these numbers were taken based on some parking prices. These are the assumptions; those were taken into consideration. So we considered that all autonomous vehicles are electronic vehicles, whereas all human-driven vehicles are non-electric vehicles. And we are considering that no particular lanes or dedicated lanes are required for AVs or classical vehicles. We are saying that those can travel together on the road. And here we are saying HGVs and LGVs are not present. And we have these scenarios that we have shown in our earlier slides. We are saying that only those options are available to the passengers. This is one of the results showing the travel time. In this, we can see that. Let's see the case of baseline, or we say no policy intervention. We can see that with the inclusion of market penetration rate, when it increases, the percentage of autonomous vehicles, when it increases, then we can see that there is a delay in travel time. It's not consistent, but there is some delay. But in other scenarios, we see that the improvement is not much. This could be because of the reason that vehicles are choosing parking conditions those were given to them. So in that, suppose vehicles are driving around. So what will happen when they will drive around on the road, then the roads may get congested and we may not get the improvement in travel time. Similar behavior can be observed for the other scenarios. This can be verified with the help of this flow diagram we are seeing here. So here we can see that in drive around scenario, the flow was reduced. It was very less, and we can see that the travel time in that case was not improved. It was almost same or little bit higher. These are the results from the travel time. So in this, most of the reviewers expected that introduction of AVs will lead to reduction in travel time, and parking behaviors may negatively affect the travel time of vehicles, and this all will be decided by the behavior of parking. So here we can see that in the second round, most of the reviewers either definitely agreed or slightly agreed with the results obtained in the first round of the Delphi results. These are the emissions results. So these are similar to the one just before me, Sasa was showing. In this, we can see that clearly when the market penetration rate of AVs increases, a decrease in the emissions can be observed. For all the scenarios, this is consistent. And these are the crashes. Conflicts are not shown in this presentation. So the method we used to calculate the crashes are similar to the one that Amna has shown. And we can see that as the market penetration rate of AVs increases, there is decrease in the crashes. Here, suppose let's take this case of drive around again. Like earlier I was showing, we see that the flow has reduced a lot and vehicles are in congested condition. So we may feel that in drive around the crashes are less, but it could be because of the flow that was observed at that locations. And the key findings, some of them are similar to the one those my colleagues have shown earlier. So delays reduce with the market penetration rate of AVs in no policy intervention, and this could change because of different policies we include. And we saw that highest delay was observed in heavy drive around and heavy return to origin and park outside scenario. Delay can increase up to 40% in drive around and heavy return to origin. The traffic flow, it can reduce up to 60% with a drive around scenario. And the main reason for this is that all roads are filled with the vehicles and there is no space to move. Hence, that traffic volume reduces a lot. This is the one I have shown earlier. So travel time reduces with market penetration rate, but the strategies those we use may diminish the improvement. And in this now, with seeing all these results, we cannot clearly say which policy will be the best. We need to test more, and yeah, that's it. We can't say which one is the best, because we with this behavior that we saw here, we can't make a clear distinguish between them. I don't know, my mouse is not sorry. Yeah, so that was the.
Thank you, Mohit, for your presentation. If there are any questions, please put up them under Q&A. Any questions for parking pricing? I would also like to just add that in our future work, we are considering to test some of the additional possible strategies that haven't been tested so far and didn't share so far in terms of the findings that we covered in today's webinar. So that goes to parking pricing policy as well. If there are no questions, I can maybe go to closing remarks. Can you stop sharing?
Yeah, I did.
Thank you. Just to present some closing remarks, some overall bigger level findings which are emerging from the work that we have been doing under Levitate, is number one, that transition phase to full fleet penetration is of high importance, and we have to prepare to manage potentially adverse impacts. Cities cannot control introduction of cabs in transport systems, but with right policy decisions, they can mitigate the negative impacts due to introduction of cabs during the transition phase, particularly. The methodologies that were developed in the project, they can be applied to test various other interventions, so they can be taken as guideline for testing various other interventions. From our study, our results are showing some irregular balance of benefits and disbenefits in transition phase, and as I mentioned earlier, that right policy decision is the key in this regard, which can potentially mitigate or minimize the negative impacts of during the transition phase. And of course, we need better knowledge of cab behaviors. We need real world operational data to be able to realistically model CAP's behaviors and analyze the impacts. And with the existing knowledge and assumptions used, results must be examined according to the assumptions. In terms of contributions of Levitate, there are a few things that I would like to highlight here, that we have analyzed city scale impacts. Our project work involves city level impacts estimation, and wider level impacts, societal level impacts. Also, we have made use of different methods, different combinations of methods have been used for estimating wider impacts, including microsimulation, mesoscopic simulation, system dynamics, Delphi, operations research. And when finding an optimal strategy, only one method may not fit for all impacts. So our findings, or the different approaches that we are using, the findings from different methods can be combined together to find an optimal strategy by the cities. Also, we have performed a test on transferability of results in one country, and which shows applicability of our approach within that country. And we are now, in future work, we are targeting to expand it in other areas as well. That's about overall final remarks. And I would also like to say, for updates, please keep checking our website. And we have several webinars planned for in next couple of months. So please keep checking the website for that. Next coming ones would be urban transport and case studies, and based on urban transport, and second one on case studies. And schedule of these two have not been finalized yet, but please keep checking our website for that. With that, can I invite all the presenters to turn on their video, so that if there are any questions or comments, we can respond to them. I can see if there are any questions. Yeah, no, I don't see any additional question, but I do see that our Twitter link was shared, and subscription to our newsletter. So please, everyone, I would request you to subscribe to our newsletters and follow our links, our website link and our Twitter link. Can we still wait for any questions that anybody would like to ask from any of the speakers? No? If not, then we can conclude here. I would say thank you everyone for joining and participating. I hope you found our presentations interesting and insightful. As I showed, we have a couple of interesting webinars coming in next couple of months. So please please keep checking our website for those. And with that, I would just like to thank again, and I hope to see you again in our next webinars. Bye-bye.